Hello. In this lecture 12, we will discuss some aspect of the application of the Considere criteria, in particular the confusion surrounding it. Then we'll move on to describe a very important concept, what I call geometric condensation, that occurs in the affine deformation limit and involves a highly stretched chain network.
All right, so I see this is always too loud. Okay. Questions? Last time we were on basically the essence of strand hardening, what it is, what it is not. There's a geometrical aspect to it. I think the lovely thing about it is, if anything, I think I was very fluid on this. If anything that's unclear, you can always review the recording again. But of course, I welcome your questions. Now, see the sensors on this. All right. So if you, I prepared an outline. If you look at the outline, we finished chapter 7, and we're on chapter 8. There is a section on 7 that I have not spoken about last time, and I should say something about it before, as part of the discussion of extension. And then on the chapter 8, we are basically dealing with the strand hardening. And today I will speak a little more, about the topics of geometrical condensation. In fact, I found a little, or if not little, quite a serious error in the book as I prepared for this part. I should mention it so that it gets updated. Okay. So I have conceptualized the idea about what strand hardening is, and by indicating that the reference frame is incorrect, because in the affine, at least when the sample is affine, the feature of strand hardening that we defined really has a lot to do with whether you still have affine deformation or not. So it really has everything to do with ability to yield or to disentangle. I know that's a molecular concept that we have not talked about yet, but allow me to suggest that the structure we have is entanglement, and the breakdown of the structure is disentanglement in some manner that we have yet to define more precisely. So maybe if this is entanglement, disentanglement probably just means that this chain starts to slide relative to the other chain, okay, in the zeroth order, so that they are no longer just graphs onto each other and be effective anymore. So that's for much later, but that's the molecular origin of yielding that we will say a lot more much later. So this part of the discussion, of course, is highly unconventional. I'm happy to receive any criticism from the community on this point, but or feedback rather. But this is what I had to offer in that part of the discussion. So for the sake of completeness, I should say a couple words about Considere criteria, very much related to the question of ability to yield versus whatnot. And this also gave me a chance to be sure that I was not misunderstood. I said in the last lecture that typically in startup extension or melt stretching, classically or conventionally, we are looking at true stress, or in fact, we very often look at the stress divided by the rate you apply as a function of time. That's what I'm repeating now. You get the zero shear envelope. I try to change the color, but the computer never can react fast enough. And then you have the so-called strand hardening that I'm reviewing for you. So the signal being above the red zero rate line is called strand hardening, if you still remember, zero rate limit. I indicated that this is true simply because your sample is not able to transition quickly enough into a non-affine state, non-affine deformation. When you have affine deformation, then you have this sample being transformed into a state that's very dense in the direction of stretching. So it becomes apple versus orange here. And that's why this reference is not right. There is a small set of literature. That's why it allows me to correct or to make sure I'm not misunderstood. There is a small part of the literature on melt stretching where the data was represented as engineering stress versus lambda. Okay, there is a set where, lo and behold, you find that indeed you will have a maximum, as I try to indicate so many times now, right? There's a maximum, there's shear, there's this. I mentioned this before, and when we talked about why engineering stress is a variable for you to see that you can lose the structure, because if you don't lose it, this should keep increasing because this term keeps increasing. The only time this can come down is this no longer increases. That's the density of the entanglement, if you like. So the fact this thing is coming down must mean that your structure has changed, in absence of which it will be monotonic. Okay? There is a subset of literature that does represent your data this way. However, there is some trouble with this representation, in the sense there were discussions about Considere criteria, so which is a very old observation of metals. If you stretch a metal, you'll find this is nothing but tensile force, okay, normalized by the area. You find tensile force could reach a maximum, and beyond it, they find the sample will neck. In other words, it will not be uniform anymore. Okay? And this causes a great deal of confusion in the sense people have used, this is a person, he wrote a paper about metal beyond the maximum is necking. And polymer people, for polymer solids and for polymer melts, also start to use this criteria and saying, oh, if there's a maximum, you should have necking. Okay? And the argument goes as follows. In the past, I have covered this part in polymer physics too, but in the last 2 years, I omitted it. But the argument goes as follows. If you have a piece of material that inherently is really showing this red curve, reaching a maximum, then the perception was if there's any defect, for example, this part being thinner than the rest of the part, okay? If it's thinner than the rest of the part, then you can see that I may argue that for the thin part, the curve will be a little lower. I exaggerated. Same material, but in theory, because this part is thinner, it will generate less stress, right? The total force will be lower because you measured your A0. Not everywhere. You measured A0 as the average number, but there is a cross-section where this A is a little smaller, then of course you will have a smaller value. So if this material reaches this point and try to march on, or rather, if this material reaches maximum, oh God, what happened? Okay, computers. Is reaching maximum. If you try to march on, it will tend to march on in this direction for sure. But for the rest of the material, it's only hitting this point, right? By definition, because the force everywhere is the same. So you can see this point will not move up, and this point is moving down, and this part must neck. Because the rest of the point does not reach the condition to even increase its lambda. So locally, this part will start to thin necessarily. And that was the argument. Okay? And I want to indicate today that this, number one, is not necessarily true. Number two, I call this causality reversal in the following sense. You know, in our doing science, causality is literally everything we do to figure out what is causing what. In this argument, which is to the best of what I could present to you, this is how we argue it. Either this sample is a little thinner, or somehow this sample was somehow weaker for some imperfection reason. One could indeed develop an argument and say, oh, this part must thin because, oh God, you see now the pen is not at the same place now. This part must thin because other part will not reach the condition to reach maximum even. So as you draw more, this part will draw more, meaning the black line will draw more, and sample will go in this direction. Oh, gee, what do I do? Let me close and reopen. The pen is not pointing in the right direction. So you see this argument says nothing about anything. In fact, it does not say Sorry for this. This is just technically. It should do well now. Yeah. This part of the sample just gets thinner. Remember, remember this curve. This is the direction of increased stretching, right? And this black part, which represents a little section here, will just keep drawing because the rest is stronger. And that's the argument that you have necking. That's the literature argument of it. What's the problem with this argument is it obviously doesn't tell you, well, if you believe this argument, you will say, sounds like there will be necking. What I can tell you is we have, or where does it neck? Here, 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 where? It doesn't say anything about it, okay? What I can tell you is the necking doesn't occur after this maximum at all. There are cases the necking simply does not occur. In other words, you could have drawing a big amount of stretching without ever reaching a condition for yield, for necking. So I call it the causality reversal in the sense, I think the problem that we're dealing with first should be to answer what causes this force to decrease. The force to decrease is only an effect. Here, it was taken as the cause. Okay, this is why I call it a causality reversal. The force drop is only the effect of something else. What is causing it to drop? Well, we know, even casually, we know yielding causes it to drop. What do you mean by yielding causes it to drop? We mean that, that maybe you are losing entanglement. Or can you lose entanglement uniformly? The short answer is yes, you can lose entanglement uniformly in the sense that you can draw while past the maximum and it still draws uniformly. Okay? So if you like, the monotonic which is just the effect of molecular events such as disentanglement, is not the cause of necking necessarily. In other words, this non-monoticity was actually caused by other events. So what I'm trying to say, I mumbled a lot here, is when we argue at this level, at the Considere level, we are at a continuum level. Okay? Obviously. All this maximum observation, that's continuum level. At continuum level, you observed non-monotonicity. And you start to claim that this non-monotonicity will produce necking. That's what the whole argument is, based on the fact that your sample is unstable against small perturbations. That's the rigorous word to say. Small perturbation meaning the sample is not perfect. Let's say my sample, some part was just slightly thinner than other part. Okay? But this line of thinking, of course, is treating an effect as the cause. It is the effect when we are looking at molecular level. When we're looking, instead of continuum level, when we're looking at molecular level, it is there we ask what is causing this force to decline, right? So the decline is an observed effect. The cause, of course, is at the molecular level. So my simplest trivial example would be a boy hit window with a piece of stone and broke the glass. Okay? So you see, oh, the window is broken. And you say, oh, the stone broke the glass. Is that fair? It's exactly that analogy. The stone didn't break the glass. The boy broke the glass. Yeah? The stone would not come from the road and fly into the window. Okay, so in science, there is this peculiarity of where you trace your cause to. Okay, the stone the stone was not the reason. This piece of stone sitting here is not the reason that window will be broken. It's because the boy threw it. So I think this, of course, is a very blunt analogy, but there is some. This is the only way I can help you to understand that the first order question is why the force could decrease. That's the more interesting question. You may say, oh, if it decreases, if I understand its origin, then I can ask if that decrease will be stable against perturbation or not, meaning small amount of a defect here, for example. And the short answer is very often our sample is not perfect, but this small perturbations never destroy the homogeneous stretching. Until much later, there could be a condition where eventually necking could occur. But that's a question for us to answer at the next level, at the level that also need to explain why the force decreases. In other words, the explanation, the Considere criteria saying there should be necking offers nothing about why the force is decreasing in the first place. They are using that decreasing as the cause, right? So I'm just repeating myself now a number of times. Cause and effect is reversed, or is, I wouldn't call it interchanged, but let's say messed up. Are you with me on this? Okay. Let's. I don't know how much better I can say about this. This is what I guess. To me, it's beyond a matter of opinion. But we all have our rights to reason. Maybe you can think a little bit and come back and reason with me later on this. Okay. So otherwise, we'll move on. The chapter 8 is largely done because it was mostly about for me to tell you that the strength hardening it need a quotation mark in the sense that the reference point is not quite right. And it's all related to what I told you several times, that in extension, the loading area keeps changing. It's not fixed. This is what produced the apple from orange as I start to stretch. As I start to stretch, I have produced a new structure, if you like. See, I know so far we talk about viscoelasticity, we talk about yielding, we talk about yielding typically is about destruction of the structure. Here is sort of like a new concept. In the limit of a fine deformation, which obviously means the structure has not been destroyed, in that limit, we actually also can alter our structure in a funny sense because we're using uniaxial extension, for example. This structure, orange, apple, or apple, orange, this structure is already different. Okay? These two structures, one is A, one is B. When I look at head-on, right? When I look at from this direction, right? So if you like, from XY direction. If I look at the XY plane, if I look at the XY plane, looking XY into it, I see a bunch of strands like this. When I look at stretching later, I see a smaller cross-section. I still have these 4 strands. So it's a different structure. That structural difference is enough to produce something like this strand hardening. Okay? All right. This is the part I have it actually discussed mainly in the appendix called geometrical condensations. So I will go slowly. So let's consider extension again, okay? So in extension, a few things are true that you can pay attention to. So for example, if you have a chain that has an end-to-end distance r, all right, then of course, in our discussion, typically, this chain is made of a number of cone segments. Sorry for anyone who such that the end-to-end distance is the number of cone segments times the cone length squared. So each of this has a little cone length. I know in polymer physics 1, you all covered this, but I think one of you guys may not have, Don may not have a lot of background on this, but it's possible to make it up. So basically, this is a Gaussian chain with end-to-end distance like so. Then, of course, if you straighten this chain, right? Can straighten it. Let's say you straighten it in the fine limit. So in other words, you hold these two ends and try to stretch until it's straightened. Okay? And you can ask, how much do you have to stretch to straighten it? Hold the two ends. Just try to stretch until it's fully straightened. It's an important concept because we're talking about extension. And you know when it's straightened, it is just a contour length of n times L, K. Lk is the cone length, right? So it came from initially this state to that state. So this stretching, the amount it required, is essentially the shape change. Remember, this is all just about shape change. So it's really just L over R. Right? So that it's just this dimension ratio to that dimension, right? Just like your R is like your L0, right? Come on. And your L0 over L is what we call lambda, or stretching ratio. Yeah? Yeah, it's all clear? I cannot do anything if this is not clear. Right? Just pretend this is your object. You initially, it is L0, and you stretch to lambda star. What is the lambda star that will give me straighten? That's just the ratio of the two lengths, right? And because of this expression and this expression, it is nothing but R over Lk, or square root of n. Okay? Okay. This part is clear. And we'll discuss a few more concepts here to eventually speak about the geometric condensation that we have start to indicate, like in here. So so this is how you stretch a chain. Let me now introduce another concept, which is the molecular thickness. A molecular cross-section. If you like to think a chain is a cylinder like this, what is the cross-section here? If I treat this chain as a finite rod, a rod of finite size of cross-section S. So this part I will not say too much. You can go back to the book. Basically, it's in its formula in chapter 2. It shows that S is packing length times the cone length. So packing length is something, I'm just copying this for you. Packing length is something we reviewed. The packing model, we introduced the concept of packing length before. So this is a molecular cross-section of a chain. What we're trying to get is the following story. If you remember, you have a chain which has a size of course, 2 Rg. Okay? And if you like, that's going to give you an area of pi Rg squared, if I think about cutting across, right? So we're going to try to figure out something quite detailed about the concept of geometrical condensation, or about the fact the chain generally is coiled, okay? So just like here, this chain, although I draw it like a U shape, but this chain actually is highly coiled. So what we will first discuss is for you to think about when I cut through and obtain this cross-section, what do I have? Maybe I should use black color because on this side I have a black. So that plane. Well, you will cut some of the red chains. Because you can see you cut some of the red chains. And there are many other chains, of course. For example, there will be some chains that I represent with a cross. There will be some other chains that I represent with triangle. Yeah? Because in that space there are many chains, not just the red chain, so that it goes to the state of a melt. Okay, each of this has a little area of S. That's what I just indicated to you. Right? I indicated that that's how you have what you have. When we did the packing model, we indicated that in this space of its own pervaded volume, how many other chains are there? How many chains are there? And that is discussed previously when we talked about packing model and discussing this on this page. I just recopied that page here for your convenience. It has to do with that pervaded volume versus each chain has a physical volume, so the ratio is how many chains are there in that volume. And the details are in the book as well as in our previous lecture. So I just need to borrow this concept of Q here, okay? And do something about it. So what I indicated is that in this pervaded volume of a chain of size Rg, you will have Q number of chains, which I defined in previously for you from packing model. Each chain, when it crosses a surface, I'm trying to figure out this. I'm trying to figure out this area of 2 pi r, what I just draw, the circle, how I fill up this area. Remember, at the end of the day, this area, if you think about it, it's all occupied by, I'm not going to use different color now, I'm just trying to give you a sense. You're all occupied by all the bonds, right? All the chains. Okay? I'm not going to draw more. Fill up the space. So I just need to count how many chains are coming into that plane then. How many chains, wrong word. How many of these backbone bonds is going through it? I know there are Q chains. I know whenever a chain passes through it once, it occupies a space of S. And furthermore, look at this now. Furthermore, suppose I consider this red chain. This red chain let's say this straight chain is cut by the plane 3 times. Okay? How many times, I don't know. Let's say it cut Q times. Okay? If it cut through Q times, Each time it occupies S amount. Each chain passes through Q times. Each time it passes, it occupies S amount, and there are Q number of chains. Lord. That will fill up the space or the area. Did I miss any? This is the number of chains that I will cut through over an area of 2 pi r g. Each chain folds onto the surface Q times. Each time it folds onto the surface, across the surface, it occupies space of S. And this I already told you what number is. This I already told you because it's a function of how long the chain is, that Q. How many chains are in your own pervaded volume depend on how long your chain is. That's the packing model. So this one says it's going to be increasing with the chain length squared in your previous discussion on the packing model. You can always go back to the recording to find out what we talked about. But these are just the results. So we will find Q number of chains. Each chain will fold an unknown Q number of times. S is known because I told you. So you ask me, what is the Q? Well, this expression derives what is Q. You will find, for example, this Q. So this Q, by definition, is nothing but pi r g squared QS, which is equation 2.39a. Okay? So you can write down in a little more detail, which is 3 quarter square root of 6 r over cone length. So which means the Q is also increasing function of chain length. Of course, the longer the chain, the more times it will return to the surface, to that given plane. It will fold back and forth, back and forth, back and forth. Okay? Yeah. Yes. Of your chain, the cross-sectional area of any chain, of your given chain. Of course, we consider all the bonds are 90 degree passing through. We don't consider, some bond, of course, will be at the angle, right? I'm not going to worry about that. I'm just assuming they are all passing through. So in other words, this is, if you take that angle into account, because it will occupy area, this is a minimum area it's occupying. So in reality, help me with this. So S, I'm using a minimum S here. If I use the S prime, which is going to be larger than S, in other words, the real result should be Q S prime that. And therefore, the real result will be Q pi r S squared. I'm just trying to figure out for myself Q S prime. And if I replace S up and down, I'll get my original Q and S over S prime. Yeah? I'm playing magic here, right? And according to this expression, this is smaller than Q. Right? So I'm claiming that in reality, my Q prime will be smaller than 3, 6. And you know what this quantity is? This quantity is described in the previous slide. Here. Okay? So this quantity actually is my lambda stretching ratio. That will be straightened, chain straightened. Sure, this is a square root of 6, if you want to be accurate. Okay. Now I can start to speak about so let me just summarize for you. Where do I do it? Well, this is your final expression, basically. Your actual Q is this, and it's smaller than this value. By amount that depends on the angle it comes in, and it comes in at all angles. Remember, this cylinder, of course, has a bigger cross-section than when it comes down vertically, okay? So my estimate of the Q here is, I call it underestimate or overestimate. Basically, the real value is going to be smaller than lambda. So let me rewrite it. The Q, I know we have a Q prime. Basically, it's smaller than 3 or 1/6 lambda max, or lambda stretching. So let me do one more thing. This one more thing is the following. So if you like the area density of bonds across a surface, I know we're going to ignore the fact the bonds can come at the different angles. Is basically 1 over S. Okay, in other words, every area of S, you have 1 bond. That's what it means, right? So that's the area density of bonds. I want to introduce another concept called area density of strands. Which is asking yourself, or strands or chains, basically, you're asking yourself, how many chains? You see, I draw how many? I have a red chain, I have a triangle chain, I have a cross chain. I draw 3 chains. But in principle, it's any number of chains. So I can ask myself, how many chains are passing through a cross-sectional area? defined by my pervaded volume, okay? And that concept is important, and it is nothing but the number of chains divided by the area, right? Okay? So if you have done that, I showed you last time that 2 pi r squared is q s small q. You'll find, because of this definition, that this expression becomes 1 equals s phi q. Or, if you like, q 1 over q is phi over gosh, this is called phi. I forgot what this is called in Greek. Psi? Yeah. So this I motivated you to accept. With this definition, we come up with this, which I rewrite is this. And it says something very, very geometrically profound, okay? Remember what Q means. Q means how many times it folded back onto the surface. So if Q is 4, it means this chain, let me redo it. If Q is 4, it means this strand come to the surface 4 times. Okay? It comes to the surface 4 times. According to my definition here, I count it as coming through the surface once. According to this definition, it came through 4 times. So equivalently, it's like this chain has only come through once. Or if you like, if I might borrow this, this would be what I would represent. This chain passed through this area 4 times, but it only is counted as 1 because it is a low-bearing chain that do you follow me? So basically, it's a chain like like this. It folds back and forth so many times, it wasted all the area in the cross-section without contributing more to the load bearing. I know that's a little bit of a stretch, but come to think about here, imagine this chain is being stretched so that it has force in this chain, okay? And you will only count this force once, so to speak, yeah? But this chain, the way I draw it here, if you want to draw it differently, this chain actually folded back several times, like this. So in fact, the best way to draw it was, I had it in the book, in fact, was to draw it basically that because I'm going to have a plan like this. So basically it folds back like that. You see, now it folds 3 times here. So this is the end of the chain. It bears some load, but it occupies 3 as much of the area it needs to in order to, since it's coiled, So if you like, the inefficiency is described exactly by Q. Or 1 over Q is the fraction that the chains are utilizing the area. Okay? I hope this part is clear to you, because otherwise I cannot proceed. Basically, you have a Gaussian coil, and I know when I draw it, I always feel it's if this is the direction of stretching, and this is the plane, and if the chain goes back many times, let me use a black color here. If the chain goes back and forth many times, you are wasting all that area. But that's the reality. So if it crosses 4 times, I would say Q is 4. And therefore, the occupancy is a fraction of 25%, if you like. Okay? I can reduce Q to 1, which means there's no more folding. Chain is fully straightened. We know when it is fully straightened. We describe it here. We need to stretch by a lambda star amount, it will be straightened. Okay? We're hoping that by the time you stretch your sample by a lambda star amount, your Q will go back to 1. In other words, it will not fold 4 times anymore. And looking at this expression here, or I rewrite it here, if you ignore the inequality sign, if you ignore that numerical factor, in my book, I have basically equated this two. How convenient, because that would be nice. You straighten to the lambda amount, all the folds go away,